Hi all. Let's see the next topic, sign magnitude multiplication of unit 3. In today's lecture, we are going to discuss about an introduction with the binary multiplication, next hardware implementation of sign magnitude multiplication along with its flowchart. So let's start with an example of binary multiplication where I want to multiply two numbers where the first number is said to be called as my multiplicand and the second one is said to be called as your multiplier. And when I perform a multiplication on these two binary numbers, I get a product. We call it as a product. So this is done using four rules of binary multiplication. We have already seen this in a binary arithmetic. So the rules are 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. So let's see an example. So when I am multiplying these two numbers 10111 multiplicand and 1010 which is a multiplier. So whenever the bit of your multiplier contains a 0, we are going to copy all zeros in our partial product. We call this as a partial product. And whenever the bit of a multiplier is a 1, the multiplicand is copied as a partial product. So this is how we perform a binary multiplication. Once you have done it for all the bits of your multiplier, all the partial products are added to get your actual product. So this is how a binary multiplication is done. So if the multiplier bit is 1, the multiplicand is copied down, otherwise zeros are copied down. Finally, the partial products are added to get the desired product. The sign of the product. How do you determine what is the sign of your product now? Depends upon the sign of your multiplicand and multiplier. If they are same signs, the multiplicand or multiplier are either both positive values or both negative values, then the sign of your product will be positive. If any one of the signs of multiplicand or multiplier is a negative, then the product sign will be a negative because plus into minus minus. So you get a negative product. Next, we'll start with the multiplication of a sign magnitude data. So in sign magnitude data, we have one bit, the most significant bit, which is called as your sign bit, where the remaining part represents your magnitude part of your data. So how do you perform a multiplication operation on a sign magnitude data? So this is the hardware implementation which tells you about how the computer hardware is organized in order to accommodate the multiplication process. So we have register B register, which is used to store your multiplicand. Okay, and the sign bit of your multiplicand is stored in a flip flop, which is called as BS. Similarly, we have Q register, which is used to store your multiplier. And the sign bit of your multiplier is stored in a flip flop called QS flip flop. And we also have one more register called A register, which is said to be called temporary register. So this register initially is initialized to all zeros. It doesn't have any contents. And there is a flip flop which is used to store the sign of your contents of A register, which is AS flip flop. Okay. Apart from this, we have a complementer and a parallel adder. We know what is a parallel adder. It is used to perform addition operation on the contents of B register and A register. And the complementer is used to transfer the contents of B register to the parallel adder, as well as it also transfers the contents of A register to the parallel adder. So the parallel adder performs an addition operation on the contents of A and B register, and that result is stored in E and A. So E is your flip flop which is used to store your carry bit, and A register stores your sum. And we also have a sequence counter. As we know, the multiplication process can also be seen as a sequence of additions. So if you look at the hardware implementation, we don't have any multiplication hardware internally present. So we are performing a multiplication with the help of sequence of addition operations with the help of a parallel adder. So we need to have a sequence counter. So this sequence counter is initialized to a value equal to the number of bits of your multiplier. So if my multiplier contains 4 bits, the sequence counter is initialized to a value 4. Okay. So as a part of your multiplication algorithm, you have to perform the logic write operation on the contents of E register, A register and Q register. So shift right on the contents of E, A, Q. That is a logical shift right. How do you perform a logical shift right? A zero is inserted into the uh, position of E flip flop, the contents of E, and whatever is the contents of E flip flop, they are transferred, the shifted right, and they replace with the most significant bit of the contents of A register. Similarly, each and every bit is shifted towards the right, and the least significant bit of the contents of A register is shifted to the most significant bit of the least significant bit of the contents of A register is shifted to the most significant bit of the contents of Q register. Like that, the contents of Q register will also be shifted towards the right, and the qnth bit is the rightmost bit or LSB bit of the contents of Q register is designated by qnth bit, that is rejected. So here, as a part of your multiplication algorithm, we are going to check what is the value of qnth bit. For that, we are representing the LSB bit of Q register as Qn. Okay. This is the hardware implementation of multiplication. So initially the multiplicand is in B and its sign bit in BS, and multiplier is in Q and its sign bit is in QS. The sequence counter is initially set to a number equal to the number of bits of your multiplier. So the counter will be decremented by 1 after performing each partial product. And whenever your counter reaches 0, the product is formed and the process stops. Now the sum of A and B forms your partial product. Now this partial product is transferred to E and A registers. After performing sum, the partial product is now stored in E and A registers. Next step, you are going to perform a shift right on the contents of E, A and Q registers, the right shift. Okay, so this is how you perform this is a hardware implementation. Next, coming to the flowchart of multiplication, your multiplicand is stored in B register and a multiplier is stored in a Q register. Say for example, I am performing a multiplication on two operands where my multiplicand is -3 and multiplier is +2. So the magnitude part of your, not the sign bit. So the sign magnitude data means you have both sign bit and magnitude. But only the magnitude part of your multiplicand is stored in a B register and the magnitude part of your multiplier is stored in the Q registers. Whereas the sign bits are stored in BS and QS flip-flops. So BS is nothing but the sign bit of your multiplicand, which is 1 because it is negative, and QS is nothing but the sign bit of your multiplier, which is 0 because this is positive. So BS and QS represents the sign bits of multiplicand and multiplier. Now A and Q, so if you see the hardware, A and Q stores the product of your multiplication. So when you are doing a multiplication, say I am taking a 5-bit multiplicand and a 4-bit multiplier, you are getting a product which is 8-bit, and this 8-bit cannot be accommodated in a single register. So the product requires two registers, A and Q. That is the reason we are using a temporary register here to hold your product also. So A and Q registers are used to store your product. So I have to identify first what should be the sign of my product. So since A and Q are my stores my product, I need to assign sign for that particular product which are stored in AS and QS. So I am performing QS XOR BS. So what is the sign bit of QS? 1. BS, sorry, QS is 0 and BS is 1. So 0 XOR 1 is 1. So 1 means negative. So this is the sign of my product. So the product is stored in AS and QS. So for both AS QS, I have to assign the sign for my product. Next step is initialization, where I have to initialize the values for A, E and sequence counter. So A is a temporary register which is initially set to all zeros, and E is a flip-flop which is also initially set to 0. And sequence counter is now initialized to a value equal to the number of bits of your multiplier. So if my multiplier is a 4 bits, so along with the sign, it will be 5 bits. So that is why I am representing n minus 1. N minus 1 means that only the magnitude part of your multiplier. So together, if I say what is the size of your multiplier, I say it as a 5 bits. But I have to consider only magnitude part. That's why I'm representing it as n minus 1. Okay. Now we are going to check the qnth bit. So qnth bit is nothing but what is qn? If you look at a hardware implementation, qn is the rightmost bit or least significant bit of the contents of the q register. So we are going to check what is the qnth bit, whether it is 1 or a 0. So suppose this is my contents of my q register, where my least significant bit designates qn, right? So what is the value of qn? 0. Since whenever it is 0, I have to perform a shift right on the contents of E register, A register and Q, E flip-flop, A and Q registers, and then I have to decrement my sequence counter by 1. So once this step is over, I have to now again check what is the value of my sequence counter after decrementing. So if it is equal to 0, that is the end of my multiplication, and whatever is in the A register and Q registers, that is my final product. If it is not equal to 0, again I have to go to the loop and again I have to check the value of Qn. Say for example, now say this is my, after performing a shift right, this is my content of my Q register and 1011. So now again I will check Qn. Uh, Qn is equal to 1. So whenever your Qn is equal to 1, you have to perform addition operation on the contents of A register and B register, and that is transferred to EA. Okay, the sum will be in A and carry will be in E. And after this, you have to also perform a shift right on the contents of E, A and Q and decrement your sequence counter by 1. And once this step is done, you have to again check the sequence counter. So this process will continue until your sequence counter is equal to 0. Whenever your sequence counter reaches 0, it means that is the end of your multiplication process and the product is stored in A register and Q register. So if I have a 10-bit product, 5 bits will be stored in A register and 5 bits will be stored in Q register. That gives my total product. So this is the algorithm for sign magnitude multiplication. So the multiplicand is in B and the multiplier is in Q and the respective signs are in BS and QS. We are going to compare the signs of A and Q. Sorry, this is not A, B and Q, and based on that we are going to set the sign for your product. Next, registers, we are going to initialize the registers A and E and they are cleared. We are making them both as zeros, and the sequence counter is set to the number of bits of your multiplier, which is n minus 1. N minus 1 represents only the magnitude part of your multiplier. Now the low order bits of the multiplier, low order bit, which is nothing but the least significant bit of the multiplier, is Qn. That is, you need to test it. If it is 1, then the multiplicand is added. The multiplicand is stored in B. It is added to the present partial product. A stores the present partial product, that both are added. And if it is 0, you are not going to do anything. You are just going to shift the contents of E, A and Q, and the sequence counter will be decremented by 1. If it is not equal to 0, then you are going to repeat the process. If the sequence counter is not equal to 0, the entire loop is repeated until a new partial product is formed. And whenever your sequence counter reaches 0, we stop the entire process. And whatever is there in the contents of A and Q, that is your actual product. And the sign bit will be in AS and QS. So this is the flowchart of multiplication of sign magnitude data. Thank you.